Now let's start with taking an example of convex surface when we are placing an object in the rarer medium. Okay, so this is our denser medium, the principal axis, refractive index mu1 and mu2 for rarer and denser. Now in this case, first of all, I'll be drawing the normal, which would be expanding the radius, right, for this whole curvature. So let us say this is our normal and object is placed here. So this be initial ray starting from object. This is the point of their intersection, so this would be angle of incidence. Now the ray, since it is traveling from rarer to denser medium, it's not going to go straight, so I'll be bending it towards the normal. Okay, so in that case ray will hit the principal axis somewhere here. Okay, now if you are still wondering that how come this ray can bend so much, consider that the object has been placed quite a bit longer distance as it is shown. Okay, now this is the formation of image. So angle of refraction would be this angle R. So see, try to focus only on the method on which I am producing the result. First of all, I'll start with step 1, that is according to Snell's law. What is Snell's law? According to Snell's law, ratio of sine of angle of incidence to the sine of angle of refraction is equal to refractive index mu, which is sin I over sin R, will be equal to, in this case, the ray is traveling from 1 to 2. That means it would be 1 mu 2. I can rewrite this thing as mu 2 over mu 1. Done. So I am left with sin I upon sin R is equal to mu 2 upon mu 1. Now we know this property that when theta is small, sin theta tends to theta and tan theta also tends to theta. That means instead of writing sin I upon sin R, I will be writing it as I upon R is equal to mu 2 over mu 1. Done. Cross multiplying, mu 1 times I is equal to mu 2 times R. Now I have to write this I and R in terms of alpha, beta and gamma. Where are those? Angle of object is alpha, image beta, and this angle which the normal makes is gamma. So I have to write I and R in terms of alpha, beta and gamma. Now try to focus on any of the triangle. Suppose take this triangle, right? In this one, this is optical center C. In this triangle, use the property that external angle of a triangle is equal to sum of two interior opposite angles. That means I would be equal to alpha plus gamma. Okay, I is alpha plus gamma, and in this triangle, gamma would be equal to R plus beta. So we have gamma is equal to R plus beta. That means R is equal to gamma minus beta, right? Putting these two values in this equation, top one, I'll get mu 1 times I, that is mu 1 times this is equal to mu 2 times what is R? Gamma minus beta. Done. So moving on, the same property by which we converted sin I to I, that is when theta is small, sin theta can be written as theta. Same way tan theta is also written as theta when theta is small. And since these laws are also vice versa true, so alpha can be written as tan alpha. So now I have mu 1 tan alpha plus tan gamma is equal to mu 2 times tan gamma minus tan beta, right? Now mu 1, what is tan alpha? I have to write it in terms of height and base. This is pole. I have to draw a height. Let us say this is the height x comma y or xy. So instead of tan alpha, I can write xy upon ox, right? Xy over ox plus tan gamma, which is xy upon xc, is equal to mu 2 times tan gamma, again xy upon xc minus tan beta. Tan beta is xy upon xi. So we can take the xy common out from both the sides and we can cancel it out. So I'll be left with mu 1 upon ox plus mu 1 upon xc, that is equal to mu 2 upon xc minus mu 2 upon xi, right? But since aperture of this curvature is very small, so you have to write this statement out. Since aperture is very small, so what is happening if aperture is small? these 2 points P and X are very close to each other. Okay, P tends to X, they are very close to each other. That means all the distances which we have measured from X can be measured from P as well. So this OX becomes, this OX can be written as OP, XC can be written as PC, XC here PC, and XI can be written as PI. So replacing the values with numerator, mu1 upon OP plus mu1 upon PC is equal to mu2 upon PC minus mu2 upon PI, right? This much is done. Now all we have to do is we have to put the values of these lengths, which are object distance, image distance, and radius of curvature. We have object distance u, but it will be taken as minus u because it is on the left side of the origin, which is our pole. Then this is radius of curvature r, and this one is image distance v. Okay, so write the values. Mu1 upon OP, OP is u, plus mu1 upon PC, which is r, is equal to mu2 upon PC, again r, minus mu2 upon PI, which is PI is v, so mu2 upon v. Now I intentionally made one mistake in this statement. Can you figure it out? This is, as I told you, that object distance which is on the left side of the optical center, that has to be taken as negative, so u would be minus here. So instead of writing negative side in the denominator side, I can write it here, right? Now bring this thing, that is mu2 upon v on this side and mu1 upon r on that side. I'll get mu2 over v minus this thing, mu1 upon u. This becomes equal to mu2 upon r is already here, and I'll be bringing mu1 upon r from that side, so that will make me make my r common denominator. So this will become mu2 minus mu1 upon r. So instead of writing that in 2 steps, which is mu2 upon r minus mu1 upon r, I can rewrite it as mu2 minus mu1 upon r. So this is our final relation between what? Object distance, image distance, radius of curvature, and respective refractive indices. This is how you have to do all those 5 derivations which we have discussed. All the 5 types are from rarer to denser, denser to rarer, either for convex or concave surface, for real or virtual images. See, what you will be given when this type of question would be asked from you, the question would be phrased like something like this: derive a relation between object distance, image distance, refractive index, and radius of curvature for, now they are specifying for convex or concave surface. Then you will get the idea that you have to draw it from convex or concave when object is placed in rarer or denser medium. Now this statement, the last part, when they say the object is placed in rarer medium, that means the derivation is from rarer to denser. And when they say like that the object is placed in denser medium, that means the object is placed in denser, so the refraction is from denser to rarer medium. So it will be mu2 to mu1 thing, right? So that is how you have to do such kind of derivations.